Hello and welcome to Vector Calculus with Sal. In this episode, we'll consider scalar line integrals. And in part 1, we'll discuss the motivations for using scalar line integrals. Consider a piece of string that has a parabolic shape. Now, we would like to know its mass. Well, mass is equal to line density times length. The length adds one complication. It's not quite a simple shape, it's parabolic. Nevertheless, we've dealt with this problem before and we know how to compute the arc length. What about the line density? Why can't we just take the line density and multiply it by the length to get the mass? Well, we could if the line density was constant, but what if instead it was a function of x and y? So that for any given point on this line, we could possibly get a different density. What do we do then? Well, here's an idea. Why don't we chop up our string into tiny pieces? Let's now zoom in into one of our small pieces. So zooming in gave us two advantages. Once we zoom into a tiny piece of the string, it looks almost like a straight line. Moreover, the density is now approximately uniform across this tiny piece of the string. Thus, once we zoom in, the shape is approximately straight, and 2, the density is approximately constant. We can then find its length by using the Pythagorean Theorem. On the bottom we have delta x, and on the right we have delta y. By the Pythagorean Theorem then, the hypotenuse delta s will be equal to the square root of delta x squared plus delta y squared. So you might be thinking, well, that's just one tiny piece. So how will we consider all of the tiny pieces that make up this whole string? And here we're going to enlist the help of an ant. Ant the insect, not your excused Aunt Sally. So we'll ask the ant to start walking along this string. We'll track the motion of this ant by using time. So it'll start at TA and end at TB. So at each instance in time, we'll radio in and ask the ant, where are you at? It'll tell us, my x position is x of t, and my y position is y of t at any given moment. Thus, r of t maps the time axis to the position of the ant. R of t, along with the beginning time and ending time, are what's called a parameterization. At some point, the ant will be in our zoomed location. Let's call that time t star. Then r of t star points to the location we are interested in. Let's find the mass of the small piece of string when the ant is walking over it at t equals t star. Since we're tracking this ant's motion by time, we could always get the distance that it travels by knowing its speed and multiplying it by the change in time. Thus, if that tiny piece of string has mass delta m, then delta m is equal to lambda, but what do we plug in for lambda? Well, the location of the ant at t star. And then multiply it by the length. The length is ds. Thus we have that delta m is equal to lambda at x of t star, coming from our parameterization, y of t star, coming from our parameterization, times delta s, which we now have a formula for by the Pythagorean Theorem. It's equal to the square root of delta x over delta t times delta t squared plus delta y over delta t times delta t squared. You might be wondering, why did we use delta t? Well, we wanted to track the location of this ant using our watch. And rather than having the ant use an odometer, we can just compute its speed and get the distances that it travels in a short amount of time. We can now factor out this delta t. I'll revert back to using r of t star rather than x and y, as it really shows you the importance of the parameterization. Now, we really want to get an accurate mass, so we're going to keep bugging this ant a lot. That means we're going to keep calling the ant almost every moment that we get. So the amount of time between calls is going to be short. We're going to take the limit as delta t goes to 0. This will then give us a small mass for a small string. But notice when taking delta t to 0, we're actually getting derivatives now of x, which depends on t, and y, which also depends on t. So this is the mass of that small piece of string. How do we get all the masses? Well, we repeat the process, doing so for each piece of string. And we do so from the beginning of the motion to the time at the end of the motion. Notice here I used different notation, but this is just a simple way to write the fact that that term here is the speed times little time. Here's the formula that we really need. So let's take this formula and apply it to this problem and compute the total mass of the string that we have with the given density that we have. In part 2 of this episode, we'll consider the first ingredient for computing scalar line integrals, and that's finding a parameterization. And notice here that I call it a parameterization and not the parameterization. Any parameterization that's fairly smooth and not complicated will work. So parameterizations are not unique, and it just depends on how fast and where we want this ant to travel along the string. Let's just choose the simplest one. So here's our time axis, and we want to map our time axis to the motion that an ant would require to travel along the string. Why don't we choose r of t is equal to t squared. That should do it. At t equals 0, we'll get that r of 0 is equal to the origin, and at t equals 1, we'll get that the position of this ant would be at the end of the string. We'll use the following parameterization with t being between 0 and 1. Don't forget the bounds of t. It's very important. Thus, at t equals 0, the ant will be at the origin and it'll travel all the way up along this line to the endpoint at 1, 1. And you might be thinking, well, is there a specific way to find parameterizations? Honestly, it takes creativity, but also a lot of practice. With experience, you'll be able to look at different lines and shapes and find the simplest and most appropriate parameterization. So keep practicing. For this very specific example, I noticed that the curve was parabolic with y equal to x squared. So I knew that if I choose x equal to t and then set y equal to t squared, since we chose x equals to t, then the parameterization that we chose should work. If the curve was circular, I would have a different answer, and there are many different types of curves. So be creative and keep practicing. Nevertheless, once you do have a parameterization, the rest of the problem is applying the formula. So in part 2, we found our parameterization. In this part, we'll find the speed of the ant, which will then give us the small distances that we require. The second ingredient is finding the speed. To get the speed, we'll have to take the derivative of our parameterization. That's going to give us the velocity. In our example, the derivative of the x component with respect to t will just be 1, and the derivative of the y component with respect to t will be 2t. Please don't forget to take the derivative of our parameterization when you want to find the speed. But now we just have the velocity. To get the speed, we want the magnitude of the velocity. Hence, the magnitude of r prime is, we now have the speed that this ant would be traveling when it's moving along this string. Notice that as time goes on, the ant's actually getting faster. Thus, here's our second ingredient in green. And if we multiply it by small dt, we'll get the small changes in distance ds. So our first ingredient thus far has been the parameterization. Our second ingredient is finding the speed and the small distances. And now our third ingredient is going to be plugging in the parameterization into our function. This part is extremely important as it's equivalent to us asking the ant to tell us what the local density is for each place that it travels across. So we definitely need to compute it. So how do we plug in the parameterization? Well, if you'll recall, this term here is x of t in our parameterization, and the second term here is y of t. Thus, we literally take this term, the x component of our parameterization, and plug it wherever we see an x. Here we only saw one instance of x. And wherever we see a y in our function, we plug it in here. And we've only seen one y in our function. Thus, lambda r of t is equal to lambda x of t y of t is equal to 7 x of t plus the square root of y of t. And what's x of t and y of t? Well, we found them up here. Simplifying, we'll get 7t plus t, since the square root of t squared is just t. Thus, plugging in our parameterization gave us that lambda of r of t is equal to 8 times t. Going back to our explanation using the ant, this is basically telling you that as we're looking at our clock, and as this ant moves up from the origin to the point 1, 1 on the parabolic curve, it's measuring a higher density, a density that increases with time as 8 times t. So let's review what we've done so far. 1 was to find the parameterization. 2 was to find the speed, as well as the small changes in distance ds. And our third ingredient was to plug in our parameterization, and we found it to be equal to 8t. So let's now put it all together in the formula. The integral bounds will come from our parameterization, the first ingredient, and our speed and small distances will come from the second ingredient, and our third ingredient will come from plugging in the parameterization. We've now used all our ingredients, plugged them into our formula, and we ended up with a simple Calc 2 integral which we could solve using U substitution. Thus, our total mass is equal to 2/3 times 5 to the 3 halves minus 1.